In the margin of an ancient book, the 17th century mathematician Fermat stated that the equation x to the n plus y to the n equals z to the n cannot be solved with non-zero integers x, y, z for any integer power n greater than 2, and then wrote, "I have discovered a truly marvelous proof that this margin is too small to contain." The statement remains unproven to this day. Computer graphics can help us visualize the nature of mathematical ideas like Fermat's theorem. Fermat's equation itself is just a cone for n equals 2, and there are many integers, such as x equals 3, y equals 4, and z equals 5, that satisfy the n equal 2 equation. If we vary n continuously, the cone changes to an inverted pyramid. The slices at constant z are two-dimensional superquadrics with exponent n. Varying n smoothly interpolates between circles and squares. The curve passes through many integers as n varies, but somehow just misses hitting any integers for integer values of n, unless n equals 2, the perfect circle. Just as one can ray trace a deformed solid by following a deformed ray through the undeformed shape, we can deform the integer grid instead of the Fermat curve. Recent attempts to understand Fermat's last theorem have explored the relationships between number theory and the algebraic geometry of surfaces. Instead of looking for intersections of a cone with a 3D grid of integers, we look for intersections of a real 2D curve with points whose coordinates are ratios of integers. In this framework, Fermat's equation extends to a two-dimensional surface embedded in the four-dimensional space called CP2, the complex projective space of two complex or four real dimensions. For each n, the surface becomes a patchwork quilt of n-squared pieces that surround the origin and extend to infinity in two complex dimensions. To visualize what is happening inside the surface, we can sweep the surface out from the outside in, or cut into the inside, or use transparent displays. For each integer power n of Fermat's equation, the surfaces have the topology of spheres with more and more teapot-like handles. To see these as the closed surfaces they really are, we transform the surface so it lies within a compact sphere. The clearer our mental picture of the problem becomes, the more likely it is that we will gain intuitive insights that will finally allow us to solve the problem. In fact, wait, I think I see a way to prove the theorem. Yes, I can prove it, but the proof is a bit long. Now, if only I could explain it to you before I run out of videotape.